is coming to us from Stanford University. So she is interested in part of the operations research group. And of course, surprise, surprise, interested in all kinds of aspects related to network science. So starting from epidemics, from network formation, and already, despite the fact you might be surprised, to see a very young person in this conference, but already clear to say and obvious to say that's a rising star in network science. So we're very fortunate and glad to see Yeganeh accepting our invitation to give this talk. So lots of interesting results already. I don't know, soda, stocks, you name it. And now we'll hear about epidemics.
Thank you. Can you hear me well?
Yes.
Yeah. Okay. Thank you so much for the kind introduction. It's a pleasure to give a talk here. I learned a lot from a lot of you, not directly, mostly from your papers and your books. And it's a pleasure to actually give a talk now in front of you. And in a high level, my research is about networks, looking at algorithms, optimization, and math modeling on networks. But today I'm going to talk about epidemics specifically. And usually when I tell people that half of my thesis is on epidemics, one of the first reactions that I get is that, but the pandemic is over. And I just want to say, yes, like COVID is over, but it impacted a lot of our lives and livelihoods. And I want to quote Larry Brilliant here, who was a lead epidemiologist in the 70s in combating the smallpox epidemic. And back then, 50 years ago, he said that outbreaks are inevitable, but pandemics are optional. So if you're going to expect new infections coming, maybe we have to develop better prediction strategies to actually mitigate them better in the future. And now that we are in this era of new technology, that we can get data and have a lot of access to kind of different data, maybe a question is that how can we leverage data correctly to predict epidemics? So with that, let me actually first just jump into the epidemic model that we're considering here. I'm going to talk about susceptible, infected, recovered model, or in short, SIR model, where in the population, every person or every node is going to have either of these three states, susceptible, infected, or recovered. And any susceptible person can transmit their state to become infected at a rate that depends on the number of contacts that are already infectious. And any infected person can recover at a rate that it depends on the infection itself. We can have different kind of definitions for that based on the model that we want to define. We can draw this recovery time from some random variable, like Poisson random variable. It could be a constant, for example. And so I forgot to say this was the SIR epidemics was introduced by Ross and Hudson in the early 1900s for the Spanish flu. So it's been around for about 100 years. And if we have access to the population and we can observe a population epidemic going on, we can ask different questions about epidemic. And I'm going to tell you what are the questions that we are interested in this talk. So we can ask how many people are going to eventually get infected, or does an outbreak happen? And if it happens, what's the probability of that event? Outbreak meaning that a super constant number of nodes getting infected. Or we can ask, what is the time evolution of epidemics? Meaning, can I recover this like lower plot by looking at some data of this people? And going back to the question of what information about the network is enough to predict these kind of questions, there have been a lot of work on it, especially because we went through a whole pandemic. I just sampling a very few subset of this work in the past 3 years on COVID. The point is that there's a whole spectrum of ways of looking at this kind of question. On one side, there are model-based approaches that when you don't know a lot about individuals' data, you make some assumption about how population behave. And on the other side, you have, on the other side, you have access to a lot of information from people, maybe by tracking their phone data, and then you can just run simulations on it. But in that case, if you have actual granular data, maybe privacy is a concern. So if not, then there is a question of how like these simulations are actually good predictor of what's happening. So today I'm going to talk about something in the middle, and I'm going to actually tell you about a simple algorithm that uses local information of a few people from the network to predict the size of outbreak, the probability of outbreak, and the time evolution of epidemic. And the main technical ingredient that we are going to use is graph limits, which I'm sure a lot of you are experts on it, but if you're not, it's a generalization for a lot of the sparse network models that you have seen. So with that, let me start to get more into the detail. The first part, I'm going to talk about estimating the final size of an epidemic and the probability of an outbreak happening. And here, I'm going to assume that the infection starts from only a few nodes, maybe one node or just a constant number of nodes. And this is a joint work with my advisor, Amin Saberi, Christian Borgs, and it has appeared in Annals of Probability. So again, let's say we had access to this whole population and we could possibly start the infection, which are the red people here, and the gray people are susceptible, and just see how many people will get infected. But instead, the main point of this result that I'm going to show you is that I only need access to local information of a few nodes to get the size of an outbreak. What do I mean by local information of a few nodes? I first sample one uniform random node from the population and look at neighborhood, meaning that like their neighbors, neighbor of neighbors, and a few more. And then if I want to, for example, know what is the final size of an infection, I need to estimate what's the chance that this person that I picked is infected. So the estimator I'm going to propose is assumes that all of the people in the boundary of this neighborhood that I picked are infected, and runs the infection and see whether that uniform random node eventually gets infected or not. So I can have another sample and do the same thing and get a few queries like that, and then see what fraction of my queries resulted in this uniform random node getting infected or not, and use that as an estimator. I'd be more precise about what the estimator is. The idea here is that just to tell you what is the information that we need. What do I mean by the local information here? So far it seems like when I take a uniform random node, I have to have access to data of all people that are at some distance from this person. So some, let's say, distance 3 from the person. But I can be smarter about it. And now I'm going to actually formally tell you what's the information that I need. So the idea again is that my goal was to estimate this relative number of people that are getting infected eventually. So if I pick a uniform random node, I need to estimate what's the chance that person is infected. And to get an idea of that, instead of looking at the whole local neighborhood and run the infection, I can run the infection backward and see if it goes far enough from that person. Eventually, the idea is that eventually, if it goes far enough, it will reach to this like first initial infected person, the patient 0, in a sense. So I start from a uniform random node, and I ask this person, tell me who are your friends? And I can only ask this kind of question from K people. I have a budget of K. So this is the first way that I use my budget. I ask the person, who are your friends? They tell me, these are my 3 friends. And I assume if all of them were infected, who would have transmitted disease? So for each of the possible edges, I draw whether these 2 people would interact before, hypothetically, their neighbor is going to recover. So it turns out that in my draw, one of these people can infect this person if they were infected first. And then I asked the same question from that person, who are your friends in the population? It turns out that there was actually one cycle here already. And again, I draw the random variables per age to see if the transmission happens or not, condition on the test that I have. And it turns out that there is a third transmission there. And now I'm going to use my third budget out of 4 budgets that I have of asking people questions. And the transmission again happens. It reaches to 4 people. And now in this scenario, it could be that the transmission stops before getting to 4 people. In this scenario that it reaches to 4 people, I'm saying that, oh, it goes back far enough in my idea of how far the infection can go. And I return the state of V as being eventually infected in this one stochastic simulation of backward infection process. It could be that the simulation goes differently. For example, this second person that was infected can have 2 different transmissions, but it already reaches to 4 people in my backward process. And again, I estimate V as being eventually infected in this scenario. I don't need to go further. But it could be that, no, I'm not testing here. I'm just asking them who are your friends. I'm looking at the final size of infection. I will get to that later. It could be that like after the first transmission, none of the friends of this second person actually infect this, so the infection stops. And in this case, I said that node V is going to be susceptible, which is actually true in my one simulation. So these are the kind of queries that I can ask from the network without knowing the whole network. And my estimator from the final size of infection is just that, taking average over the queries. If 70% of the time I see that backward process reaches to K people, I say that my estimation of final size of infection is that 70% of people are going to get infected. Is it clear what's the algorithms? Okay. So if there is no question about the algorithm, I'm going to tell you about like some key features of this algorithm. First is that the running time so far just depends on K and maybe the average degree. It doesn't depend on the number of nodes of the network. I can be smart about how I implement it to make it a constant time. And it doesn't assume anything about the structure of the network. It specifically doesn't need the network to be locally tree-like. And it can be implemented in a way that preserves edge differential privacy, which is kind of a newish definition by Dork and Roth, but it has been a lot more it's a new topic that's very a lot of tech companies care about it nowadays. But the main feature of this local estimator is that if I start with a uniform random node who is initially infected, and my epidemic is a SIR process with constant recovery time, then a constant number of queries to this estimator gives enough information to estimate the probability and relative size of an outbreak for some networks. I will be more specific about the conditions that I need, but under some general assumption about the network, this backward process is actually a good estimator for probability and size of an outbreak. And by outbreak, again, I mean that a super constant number of nodes are getting infected eventually. Okay. So more formally, the theorem says that if I have a sequence of graphs, so like our result is asymptotic. If I have a sequence of graphs that has a limit, I will tell you what does that mean, but it's just a way of defining asymptotics about graphs. And if I look at the final size of infection, the final number of people that are in the recovered state, then there exists some threshold PC and some function of the transmission probability zeta of p that the final number of infection converges to a 2-atom random variable. It's either 0, meaning that I don't have any large outbreak, or it's zeta p. So in other words, the infection either dies out or the number of infected people is zeta p times n plus some error terms. And actually the same zeta p is the probability of outbreak if I start from a uniform random node. And then going back again to this local estimator. So far, I'm not saying anything about estimation. I'm just saying what's the convergence of this final size of infection. But I can get an estimator of that constant zeta p by looking at these local samples that I told you, the backward process. And that would be a good estimate. If I need to get an epsilon approximation of this zeta p, I only need Q epsilon queries. It doesn't depend on the size of the network as it grows. Is it clear what is there? Yes.
But you always underestimate.
Yes. I always underestimate, but it gets close enough. If I go there. That's a good observation, right? So because I start with a node and go backward for only a constant number of time, and if it reaches to that, I always say this person is going to be finally infected. So it's overestimation, right? Sorry, I said it wrong. Yeah, it's overestimation always. Yeah. So, yeah. So if not, I'm going to tell you more about the conditions I need about the graph. There are two terms here I'm going to define. One is a convergent graphs. And the second is what I mean by large set expanders or expanders in general. So the first part, graph convergence, is kind of a way to define asymptotics for graphs. And we had asymptotics for numbers for hundreds of years. And random variables, it's a very natural way to define the same kind of asymptotics for graphs. So let's say I start with some simple grid graph with crosses. And what's a natural way you would make this graph larger and larger that it looks kind of similar? I would just grow the size. And intuitively, I would say families of graphs with growing size belong to the same limit if I look at a uniform random node or a typical node and root the graph from that vertex, then the local neighborhood gives a distribution over all different motifs or all different rooted graphs that you have, and that distribution converges. Yes.
How do you exactly define this?
No, I haven't defined this actually. So this was a definition by Benjamin and Schramm about 20 years ago. And Remco has a great book on it. You can look at it. I've learned all about graph limits from his book. So it has been studied a lot in mathematics and probability theory. But maybe we can also study it from algorithmic point of view. The good thing about this graph limit is that, so I just show you a simple example with grid, but actually a lot of the sparse network models that you know has a graph limit. There's a trainee, configuration model, preferential attachment, up to household models. And I don't want to go through all of these models, but my point is that if you don't want to work with graph limit, maybe you have to first choose a different network model for your population. And then based on that, you have to then deal with different parameters for each model to see how the epidemic look like on it. Instead, maybe you can use graph limits and have like a meta theorem for all of this. So the second condition that I needed about these graphs that I told you was expansion, or I need the graph to be, the network to be well connected. The definition of expansion says that if I want to disconnect a set of nodes from the rest of the graph, then I need to remove linearly as many edges as in the smaller component. And actually, a lot of these graph models that I showed you in the previous slide are good expanders, or they are well connected. And if I look at the local city, maybe it's probably well connected as well. And what we actually need is weaker than this definition. We only need the condition on this condition on large sets. We only need, if a set has a size of linear compared to the whole graph, I only need those sets have a large expansion. So I only need to, if for example, I want to disconnect 10% of the population from the rest, I want to like also remove a good fraction of edges to be that possible. It's not like we have 2 clicks and 1 edge between them in our population. Yes.
I know the model, but not everyone knows the household model. So if it works.
Yeah, so yeah, I mean, like today maybe it's not, I didn't want to go through the models, but the thing is that a lot of these previous models here, not the last 2, but the first 4 are locally tree-like when they're sparse. And these are not very realistic when we have actual social network. They don't have, like, social network had triangles and none of this had. And the idea with household model was to fix that. So you would blow up a vertex with any structure that you want. It could be triangles, cliques, or any connected network that you want. That would be a household model. So why do I need this well-connectedness? Is because my goal was to only look at local information about the graph and say something about the whole network. And local information alone is not enough if I don't know anything about the connectivity of the graph. It's just because of this simple example. On one side, I have a 4 regular random graph on a large network. And on the other side, I have 4 regular random graphs on networks of size log n. And locally, they look the same. If I route it from one node, they look the same. And if only one person initially was infected in the graph, the outbreak behavior would be very different. In the left side, for sure, it's not going to be larger than log n, but if my transmission rate is high enough, on the right-hand side, it could reach to many people. So just local information is not enough. And I need some sort of connectivity assumption about the network to say something about the global behavior of epidemic by just looking at this local backward process that I had. That's why we had this expansion kind of thing. Yes?
Size is number of edges?
Oh, size is just the number of vertices, or the number of edges is 4 times that. 2 times that. Yes, sorry. Yeah. So if there is no more question about the assumptions that we have, I can give you some general ideas about the proof. But if there is question, please ask me now. Yes.
So why the outbreak dynamics are substantially?
Okay. So I'm thinking of epidemics that start from patient 0, 1 node, meaning that one uniform random node in these networks are infected initially, and it goes and then I wait until the epidemics finish. So in the left-hand side, one uniform random node would lie in one of these components. And the most it can get the infection out to is log n, because there's no edge between different, let's say these are like different households that they don't interact with each other. But on the right-hand side, if my transmission rate is high enough, let's say for sure any 2 connection can transmit the disease, then everybody is going to get infected, which means n people are going to get infected, or 100% of my population are going to get infected. So it's very different. On the left is always asymptotically 0% of people are getting infected. On the right, sometimes it's constant fraction. Does that make sense?
So on the left, is that one graph or 4 graphs?
No, it's one graph with 4 components, or five components.
I mean, it's random graphs. I think that's why I have this question.
So each of the small ones are random graphs, but it's a collection of them. It's a collection of small population that they don't interact with different each other, but within themselves they do. Yeah. The well connection is more than the graph is connected. I can have 2 clicks with just 1 edge between them, or if I just add 1 edge here, it doesn't change the probability of getting infection to all the population. Yes. Yes, I need the expansion. Yeah. For this first part. Okay. Good. Yes.
You can estimate the design by a finite
epsilon approximations with the size by a higher number of views. Do you, something of which you have a bound, the number of views you need as a function of epsilon?
The number of queries I need as a function of epsilon is just coming from like a Chernoff bound. So it's going to grow with 1 over epsilon to the power x. Yeah, but then there is also another parameter in my algorithm, which was this looking at k number of people. That part of it, I can't easily bound it with epsilon. It depends on the graph limit.
And in order to give like perfect reconstruction of the size, you know how you should scale the number of periods, like log n or like n.
For perfect construction, then you need to know exactly everybody state, no?
But in perfect density, I mean size divided by n. You should get that exactly.
So here I'm estimating that the density, like the relative size of, yes, within epsilon, yeah.
Epsilon to 0,
Mm-hmm.
or you go to scale.
Oh, okay. No, I'm thinking epsilon as a constant. It doesn't go to 0, but it's interesting to see what happens if epsilon goes to 0. Yeah. Okay. So maybe in the next few minutes, like next 10 minutes or so, I try to give some ideas about the proof, and then I talk about the generalization of the results that I told you so far. So the proof relies on a structure theorem about the transmission network. I want to like give you a theorem that describes the global picture of people's transmission just by looking at this local structure. And what do I mean by transmission network? I have people's network connection. And for each edge, there is 2 possibilities of infection transmission before the infection starts. So I can have bidirected edges, potentially. And I draw each of them independently with the transmission probability P, which now the directed edges shows one realization of infection transmission. So for example, if I have a bidirected edge like there, then it means that both of these people can potentially infect each other. It just matters who gets the infection first. Deterministic recovery. Exactly. In this part, I'm just looking at deterministic recovery. It's a great question. Yeah. So I have now this one realization of transmission network, and I want to study its combinatorial structure in a way. And there are 2 quantities that are important for me for each vertex. There is the out component in this directed graph, which are the nodes that would get infected eventually if V is the first person getting infected. So all these red people are the nodes that are eventually getting infection from V, if that's the patient 0. Then I also care about the in component, which is just the reverse of that. So instead of looking at the edges coming out of V, I look at the edges going to V. And these are the nodes that can potentially infect V if they're the patient 0. So the blue nodes here in the graph. So these 2 quantities are important because, so if, for example, out component of V is large, I know that this person is a super spreader in my realization in a sense. And if the blue component is large, they have a high risk of getting infection eventually. So what is this structure theorem that I tell you about? There are 2 parts about it. First, we show that there exists a threshold such that if the transmission rate is lower than that threshold, then the directed graph that I get out of this transmission network is with high probability all just disconnected components that are small. So for every node with high probability, the out component and in component are small. But then the more interesting part is when we are higher than that threshold. And in that case, we show there exists a bow tie structure. And what is that? First of all, it looks like a bow tie. And then there are a few components of this bow tie that I'm going to walk you through. First is the middle part, is this giant part that we showed is unique. And it's a strongly connected component, meaning that every two pairs of nodes have a directed path to each other. What does that mean in terms of epidemic is that any person gets infected in this middle part, it will transmit the disease eventually to all of that tie of the bow, in a sense. Then there are all these nodes in the red, the middle part plus the right wing, that these are the nodes that are going to get infected in any outbreak out of this like transmission network. So again, any node in this middle part gets infected. Okay. Any node out of this middle part gets infected is going to transmit the disease first to this part and then eventually to all of the right part. Even any node on the left getting infected is going to do the same thing. Then there is the left part of it, the SCC minus. These are the nodes that lead to an outbreak in this realization of transmission network. Then there's the rest of the graph, and these are the nodes that have small in component and out component, so we kind of don't care about them in epidemic sense. And so far, I'm just describing what is a bow-tie structure, and now I'm going to tell you more about the result that we have about them. So for the same set of network that I told you, the result then we show that if the transmission probability is higher than the threshold, then this bow-tie structure exists. But also there is more. What is interesting is that for any uniform random node V, if I take out the middle component from this whole graph, what remains is going to be just a small component with high probability. So why I care about that? Because again, my goal was to estimate, for example, the final size of infection, which would be the fraction of node in the red that I showed you. And to see if a node is in that part of the graph, I don't need to know the whole graph. I just need to know if its in component is larger than some constant with this result. So if it's larger than some large constant, then with high probability it's going to be in the red part of the graph. So I don't need to track down the whole network. Also, we showed that the size of the relative size of people in red, blue, and the middle part converges. We need that because so far what I showed you was for one realization of transmission network. I can have different realizations that the set of nodes in each part changes, maybe the size changes. But then if we know that the size actually converges, the number of people in each part converges, then I know that the final size of outbreak, if it happens, is going to converge. So this exactly means that either the infection dies out, meaning that I leave my initial infected node is in one of these purple components, or it's going to lead to an outbreak which would have the size of this red part plus some error terms. So the idea clear so far. Okay. I can show you the formal result. The size of people, so like in this, let's start with this part. So the size of people in the outbreak in the red part of the graph, also the size of people in the blue part, which are the people that lead to an outbreak, converges to some constant zeta p. The size of people in the middle part converges to some other constant. And the rest of the graph, if we take out that middle part, are converging to 0. Yes.
So what was it like the sampling?
Those are the sampling, the transmission probabilities, right?
Do you know this estimate also for the maximum out component minus CC1 plus?
Can you repeat your question?
Is this inequality also true if you take the maximum of volume?
Oh, maximum? No, no, it's not true.
It's not true.
If it takes maximum over RV, it's not true, I think. But I haven't proved it, but I think it's not true. But if I take uniform random net, then it's true.
If it would be of the order n, you should be able to see it as well, right?
Yeah, I can have like one worst case node that's. Oh, I don't think it's order n. Okay. Yeah, if I divide it by n, it's true. But I was talking more about that like a uniform random node without this SSC has constant component with high probability. That is not true. Right. Yeah. Yes.
Do you know what's happened exactly at threshold?
No, no, we don't know what happens at threshold. Yeah, that's a question to ask. Yeah. And this bow-tie structure that I told you about was actually named about 20 years ago by Brother et al. When they look at the web graph empirically, and they saw this like bow-tie phenomena. And it has been actually seen in other networks, like financial networks. And theoretically, it has been proved that it exists on a lot of these random graph models, like Shreni configuration models. And in a sense, the result that we have is for expanders, but in a sense, it generalizes these previous observations. So with that, maybe I look at some small simulation. So one question you could ask is that how large should I explore in my local neighborhood? How large should this K be? And here we looked at the empirical data set from Copenhagen during the flu epidemic back in 2019. They tracked students' Bluetooth data of about 700 people, and they say an age exists if their distance within a time period was less than 6 feet. And it's an evolving network. It's a bit different from our setting, but we just work with it. And here I'm looking at estimating the probability of an outbreak. And in the red line, I simulate the infection on the whole graph. And I see what's the probability that an outbreak happens. And then in the blue part, I'm fixing the number of queries that I get to the graph. It's always 10, but I'm changing how many people at each query I'm going to track down. So like how far my backward process is going. And actually when it reaches to 3 people, the true probability of infection lies within the confidence interval of our estimate. And this kind of evidence of local information is enough has been seen in practice actually for COVID-19 vaccination. There was a paper that they compared vaccinating with demographic versus vaccinating with local information of people. And the second one was better, but yeah. So now let me just tell you a little bit about generalization of the infections that we have. So far, I told you results about a simple epidemic model when recovery time is a constant. But I can have different recovery times, like it can be drawn from a Poisson random process. But my initial condition here has to be kind of more relaxed from what I told you because of that example with one giant graph and smaller graphs. Here I'm assuming any node is infected with a fixed probability alpha. This alpha is maybe small. And in a way, I'm thinking that I'm kind of past the initial phase of epidemic and already alpha fraction of people are infected, and I want to see what would happen in the future. What's the time evolution of epidemics? And again, going to that picture, I could again simulate and get that whole time evolution. But instead, you're again saying that local information of a few nodes is enough. And here, the local information is again neighbor and neighbor of neighbors, but I kind of do the simulation a bit differently. I look at the local neighborhood of a node and see if a person is already infected in that local neighborhood and run the simulation there. And do the same thing for another node. And I look at the fraction of people in each of the 3 states of SIR, and that's my estimator. Again, I could do this with the backward process to get information of a fewer people. So when I draw this backward process, I can also draw the time on each edge, the times that they contact each other. For example, if it's a Poisson time process, I draw the times, And in this one sample, for example, after 4 days, my node of interest, node V, is getting infected. I also draw the recovery times. And after 7 days, they become recovered. I could have, again, like different kind of simulation in each of the draws. And that gives me right estimator of the infection at some fixed time t from now. And this is the main result. It's ongoing work. Remco is there, and Christian and Amin. So again, there exists constant Q epsilon, the number of queries, and K epsilon, how far I can go. That if I get Q epsilon queries with this budget K epsilon of people that I can visit, then the size of infection at time t would be recovered with some epsilon error. And then again, I can also think about the final size of infection in the same manner that I estimated in the first part. Yeah. Here, I forgot to tell you that I have access to testing here because I want to know if in the local neighborhood that I'm exploring, if somebody is initially infected or not, which has, for each person, has an alpha% chance. So if there is no question, we can wrap up. So the main message this talk was that with some simple local algorithm, we can estimate the final size, probability, and time evolution of epidemics. There were two regimes that we looked at. One was, well, the initial condition is that the infected nodes initially are well mixed, spread out through the network. And in that case, we said local information is enough to get the time evolution. And if the initial condition is more restricted, you're studying from a single node, then under some condition about the network, the well-connectedness, then we can estimate the final behavior, final size, and the probability of an outbreak. We still don't know what would happen about, if we can say something about the time evolution, if you start from single node and we have some connectivity assumption about the network. And with that, I kind of want to wrap up because I just want to have one more thing to say. So I'm really interested to see the application of graph limit in other areas that are more applied. And recently I've been working on network games and looking at graph neural networks with this graph limit perspective. But I'd be happy to also see it in other applied areas. And I think there's a lot of potential of these techniques there. And with that, I thank you, and I'd be happy to get any questions.